Okay, I'm going to go ahead and get started. Hello, everyone. Thanks for joining. My name is Jeff Sale. Can everyone hear me okay?
Yep, sounds good, Jeff.
Great, thanks. Just a little bit of house cleaning before we get started. This is an Exceed event. Oh, I didn't update the event itself. But we want to make sure everyone's aware of the Exceed Code of Conduct when attending these webinars. And if I can ask folks, and if I can ask folks to self-register, or mark their attendance by logging into the Exceed user portal and browsing to the course calendar and then scrolling down where you'll see a listing of your previous training classes. That makes my job a little bit easier in tracking attendance so we can report to Exceed. But okay, I want to start off by introducing Abe. Abe Stern is an NVIDIA solutions architect. He got his PhD in computational chemistry from the University of South Florida and did a postdoc at UC Irvine. He's focused on higher education and research, and his interests lie at the intersection of scientific computing and machine learning, especially as applied to problems in the chemistry and material science domain. So with that, I will go ahead and mute myself and stop sharing and take it away, Abe.
Thanks very much, Jeff. Share my screen here. Hopefully you can see the slide. Can you confirm if you can see the slide?
Yes.
Yep.
Great.
Yes.
Thank you. All right. Thanks so much. Okay, great. So thanks, Jeff. My name's Abe Stern. I'm actually a data scientist at NVIDIA on the Higher Education and Research Solution Architecture team. So it's the team of solution architect, but formally I'm a data scientist. As Jeff said, my background's in computational chemistry. And at NVIDIA, I tend to work at the intersection of scientific computing and AI, particularly on problems where machine learning or artificial intelligence is applied in the chemistry domain. So today I will be talking about RAPIDS and CUDA-Python. So in RAPIDS, we have a suite of machine learning libraries and tools, particularly for manipulating data frames. Okay, so if you've used pandas before, RAPIDS is on one hand a drop-in replacement, a GPU accelerated drop-in replacement for pandas for GPU accelerated data frame operations, manipulations. And we'll also be talking about CUDA-Python, so particularly the library Numba, which exposes the CUDA programming API. So you can get GPU acceleration, you expose the CUDA API so you can be programming for the GPU in CUDA right from Python. So you can do this from a Jupyter notebook. So pretty exciting stuff, I think. But these are both Python libraries, and this is a scientific computing forum. So let's set the stage a little bit and motivate why we'd be talking about Python for scientific computing. So one of the exciting trends that we're seeing in high-performance computing is that the domains of those leveraging high-performance computing resources is broadening. So traditionally, we think of high-performance, those users of high-performance computing machines, these are coming from domains like computational chemistry, computational physics, engineering, doing fluid dynamics, maybe weather climate simulation. But increasingly, we were seeing other domains also start to use high-performance computing. And in particular, I'm talking about machine learning, deep learning, and increasingly, scientific visualization leveraging high-performance computing resources. So this has put NVIDIA sort of front and center. These are two of our kind of core domains that we accelerate, that is machine learning, deep learning, and scientific computing. And you can see that's reflected in the fraction of machines on the top 500 that are GPU accelerated. So at SC9, as of SC19, we accelerate 41% of the machines on the top 500 list. That is the list of 500 fastest machines in the world, or at least those are the submitted benchmarks, including the world's fastest Summit and second fastest Sierra, sitting at Oak Ridge and Lawrence Livermore. So what's exciting is that these aren't kind of disparate domains, meaning it's not just people doing machine learning and, with blinders on, and they're doing basic machine learning research using HPC resources. What's really exciting is sort of the confluence of both of these domains coming together, right? Where AI is now complementing traditional algorithms in scientific computing. So I'll give you an example. So in the business of lead discovery, drug discovery, the task is to identify new compounds, new molecular structures with certain properties, either material properties or maybe a binding activity to a certain protein or something like this. Of course, if we are approaching this the traditional way, we know how to go from structure, that is, given a chemical structure, we know how to compute many of these properties. We can solve nearly exactly the Schrodinger equation, solve for the electronic structure, and compute those properties. The problem is twofold, really. The calculations that I'm referring to are exceedingly expensive, and the chemical space, that is the number of possible compounds out there that we would have to screen, the number of possible structures that we would have to compute properties for, the size of chemical space is overwhelmingly vast. So this makes intractable sort of just brute force approach where we would just screen all the possible structures and find the ones that we want. So what researchers have done is use AI, use a variational autoencoder to invert the problem. So they've developed a technique where you can specify a property, and using a variational autoencoder, a trained model, the model from the property will generate possible structures that might match those target properties that you're interested in. Another example from molecular dynamics. So here, those of you familiar, this will be reviewed, but the task of molecular dynamics is to basically look at the structure and dynamics of a chemical system at the atomic level. And to do this, we rely on a calculation of the interaction energies between all the atoms in the system. And there are various levels of theory accuracy that you could use to compute those interaction energies, all the way from a coarse, simple to compute empirical description of the energies, all the way up to a full treatment of the electronic structures and electron correlation and a super accurate way of computing the interaction energies. And then eventually you're going to use the interaction energies to integrate Newton's equations of motion and get a picture of the motions of all these atoms. And from this, the dynamics of the chemical system, you're learning something about the system that you're studying. So what researchers have done is parameterize, train a model, an AI model, to reproduce high level of theory electronic structure calculations at a fraction of the cost. That is, using a set of DFT level configurations. They've trained a machine learning model to approximate the interaction energy for those pairs of atoms. Okay, so they've trained a DFT level interaction energy in this machine learning model. What that buys you is the fact that inferring from a machine learned model, you can do at literally 300,000 times faster, roughly a millionth of the computational expense than as compared to a full treatment of the electronic structure problem. So you can imagine if you can compute those interaction energies 300,000 times faster, then this unlocks the possibility of doing longer scale simulations, larger system sizes, that is more atoms, and dramatically increases the kind of science that you can start doing with these types of simulations. And I should say this work is Adrian Roykberg, Justin Smith, and Alexander Isayev. So these are core to us: scientific computing, machine learning, deep learning, and we're committed to accelerating science. And so you can see here from a basket of applications that I'm sure you recognize: Amber, Chroma, LAMPS, Milk, NAMD, Quantum Espresso. You can see how our approach to GPU accelerated computing has picked up where Moore's law has left off. And we do this not only by delivering great hardware, but there's a rich software stack underneath that. And before we get into our main content with RAPIDS and CUDA-Python, I want to make sure you're aware of some of the key components of our software stack. So of course, the bottom row of the stack, I'm showing the hardware, because underneath everything is our hardware. But the software stack really begins with CUDA. CUDA is the primary programming API for GPUs and accessible through C, C++, and Fortran. And on top of that, we build a whole suite of libraries that you can further build applications on. So the GPU accelerated libraries are grouped here for illustration into machine learning. And this is where the RAPIDS, cuDF data frame, GPU accelerated data frames, cuML for GPU accelerated machine learning libraries, graph analytics. And then we have our deep learning libraries. Also, if you want to roll your own, so to speak, could call these libraries directly from C, C++. These are cuDNN. All the major frameworks, of course, are leveraging cuDNN under the hood. So if you're using a framework like TensorFlow or PyTorch, under the hood, they're, of course, calling cuDNN. Cutlass, TensorRT for inference. In the box labeled HPC, we have an interesting programming API called OpenACC, which I'll touch on briefly in one moment, but also a suite of scientific computing libraries. So let's double click on some of the what I consider core scientific computing libraries. So these libraries really leverage domains, things that are widely used in scientific computing. So several linear algebra routines. For example, cuBLAS provides complete support for all 152 standard BLAS routines. cuSparse is a library that contains basic linear algebra subroutines for handling sparse matrices. cuFFT, GPU accelerated Fourier transforms. What else? cuSolver contains LAPACK-like features for matrix factorization, triangular solve routines for dense matrices, a sparsely square solver, eigensolvers, matrix factorization such as LU decomposition, QR decomposition, singular value decomposition, Cholesky decomposition, and more. So check out docs.nvidia.com. Look for at the broad number of GPU accelerated libraries we offer. and use them. We built them for this community. So check it out. So as I mentioned, it spans domains, and a lot of the GPU accelerated applications that you're using probably already are leveraging a lot of these libraries under the hood. So if you're maybe not necessarily programming, you may want to just check out the applications that are already GPU accelerated. So check out the GPU accelerated applications catalog, where already there are 600 accelerated applications that have some degree or another of GPU acceleration under the hood. So OpenACC, this is a different programming model. It's a directives-based programming model. Those of you who have programmed in OpenMP are probably familiar with this paradigm. And at its core, it's a directives-based programming paradigm. So we use compiler directives, and these are essentially hints to the compiler to suggest ways in which we could parallelize the routine. So the nice thing is that it's very simple to program, and you get a single code base. If the compiler that you're using doesn't recognize the compiler directives that you're trying to use, they're safely ignored. So you have a single code base, and it's portable. You can target multi-thread CPUs, not only NVIDIA GPUs, but other GPUs as well. So single code base, simple to use. With a few lines of code, you can potentially get orders of magnitude speed up. So certainly check out OpenACC, C, C++, and Fortran. And applications that you're probably familiar with are using them. So Gaussian and VASP both use OpenACC directives for some parts of their algorithm, some paths through their codes to get GPU acceleration. Okay, so main content. So I'm going to start by talking about Numba. So Numba, with the Python library Numba, we expose essentially the CUDA programming API directly in Python. So we actually have both a high-level API that we can, I'll show later, we can simply code universal. A lot of the heavy lifting is done for us, but we also have the flexibility of a very low-level API with CUDA syntax, CUDA provided variables, and this gives us a tremendous amount of power and flexibility in that we are really doing GPU programming in CUDA in more or less native Python. So no need to leave even the Jupyter notebook or Python source code or compile some extra C library and call the C from Python. No complications like that. And the same is true for the data movement. With the high-level API for Numba, data movement is handled automatically. But we also do expose fine-grained control over data movement. So if we'd like, we can move the data manually. So how does the core is a just-in-time compiled CUDA kernel. So we use a Python decorator that I'm showing here, CUDA JIT, just-in-time compiled. So this is defining a CUDA kernel that will be compiled before execution the first time. As I mentioned, we have CUDA provided variables, and then we can operate on NumPy arrays or data structures in a very familiar Python way, and expose all the power of GPU accelerated computing right from Python. So we're going to tear apart this kernel a little bit. So I think what we're going to do is introduce the core concepts around CUDA programming, because you actually are programming in CUDA. So let's introduce essentially the basics of CUDA. So of course, GPUs do work in parallel, and the work itself is performed in a thread. So I'm highlighting in green a single thread. Many threads run in parallel, and we refer to a collection of threads as a block. Okay, so there's a hierarchy. We have the threads, and then we have a block. In general, there are multiple blocks, and we call the collection of blocks a grid. Okay, so we have thread in white, blue, we have the blocks, and the collection of blocks we call the grid. The actual program that runs on the GPU is called the kernel. So highlighted in green, we have perform work. That is going to be the code that executes on the GPU. That's the kernel. And we launch kernels with an execution configuration. And there's a special syntax associated with that execution configuration, because this is a slightly different model. So here, that syntax is actually the C syntax. That's the extension that CUDA adds to the C programming language. So we have the triple angle brackets between the name of the function and the function parameters. So we have perform work, then we have the launch configuration 2, 4. Okay. In Python, that launch configuration is actually square brackets, which we'll show you in a second. And this launch configuration specifies the number of blocks, in this case 2. I want to launch this particular kernel with 2 blocks, and I want each block to have 4 threads. Okay, so that together, 2 blocks, 4 threads, that is my launch configuration. And every block in the grid contains 4 threads. Okay, so as we said, the work is performed inside the threads. Each thread executes the program. So when the threads wake up, we have to have some mechanism of identifying which thread, which block we're in. And these are the CUDA provided variables. So when each thread wakes up, they're going to have an instantiation of these CUDA provided variables that define these. Okay, so grid dim is the first CUDA provided variable. So this is provided initialized already for you. And grid dim refers to the dimension of the grid. So in this case, this is specified by the launch configuration. So we asked for 2 blocks, so the grid dim is 2. We also have block index. Now the block index tells us which the index of the current block that we're executing in. So all the threads that are within the block highlighted in green, okay, the left block, will wake up with block index.x set to 0. And when a thread in the right-hand block wakes up, each of those threads will wake up with block index.x set to 1. Okay? So similarly, we have block dim. So the block dim tells us the dimensions of the thread block. So in this case, I've asked for there to be 4 threads in this per block. My launch configuration is 2 blocks, 4 threads. So I wake up with block dim.x set to 4. And all blocks have the same configuration, the same thread block configuration. So all blocks are going to wake up with block dim set to 4. Okay, and finally we have thread index. Thread index tells us the index within the block that we're executing. So in the left block we have 0, 1, 2, and 3. And importantly, this is relative to the block. So in the second block, this is block index 1. We reset, and that thread index, again, is 0 indexed. So we have thread index 0, 1, 2, and 3. Okay, hopefully that's clear. So now the task is to map this thread block hierarchy to some work. So the most basic case that we could have is a linear array of data. So in this case, on the top panel, I'm showing a 1D array of data, and it's indexed 0 through 7. Okay, so I have one index 0 through 7 mapping into some data, and I have this thread block hierarchy given with our CUDA provided variables, and I need to map the threads to that data array to do some work. Typically, this is done via this formula, but I'm showing thread index plus block index times block dim. This is a very standard way of mapping the thread block hierarchy into a linear array, and you'll see this over and over and over again. It's not necessarily how it has to be done, but it's an extremely common way, and so it's an important case to remember, because it's maybe not immediately obvious how to map the thread block hierarchy to a standard array of work. Okay, so thread index plus block index times block dim. That's a formula that should be seared into your memory. And let's see how this works with our thread block hierarchy. So for that first thread, as we know, that has a thread index of 0, and it's a block index of 0 because it's the first thread in the first block. So it's trivial in this case. 0 times 0 plus thread index 0 is 0. And so naturally, we start at the first element of our data array. As we progress through the first block, notice that second term, block index times block dim, because we're multiplying by the block index, that second term, block index times block dim, stays constant within the block, right? So for these first 4 threads, we have that second term fixed at 0. 0 times 4 is 0. And so these first 4 threads map, using thread index, map to the first elements of our data array. When we move into the second block, now we have block index of 1. Our thread index resets to 0. That second term, 1 times 4, block index times block dim, 1 times 4 is now 4, and it's fixed at 4 for this block. So as we step through that thread index of 0 plus 4 is 4. Thread index of 1 plus 4 is 5. Thread index of 2 plus 4 is 6. And so on. So hopefully you can see how this formula strides through the block dim, and we can map a linear array of data with our thread block hierarchy. So I should mention that the 1D case, where we have dimensional array of blocks and a one-dimensional array of threads, is the simplest case. We can have higher dimensional, up to 2 and 3 dimensional grids and 2 or 3 dimensional thread blocks as well. So here I'm showing you an example of, I guess, an illustration of what it would look like to have a 2-dimensional thread block within the context of our two blocks for our grid. Okay, so you can see in the launch configuration, I'm specifying 2, that tuple 4 by 4. So I'm asking for a 2D thread block where I have 4 threads by 4 threads. So in this case, I'm going to have CUDA provided variables, not only thread index.x, but also thread index.y. So you can see for the thread I have highlighted, I have thread index.y initialized at 2, and I have thread index.x initialized at 1. So that particular thread would be given by those CUDA provided variables, thread index.x, thread index.y. And of course, if I specified a 3-dimensional grid, I would also have thread index.z. And the same is true of our block indices. We can have, I've been showing examples with block index.x, but we could also have a 2-dimensional grid where I had block index.y and also block index.z. And this flexibility, you can imagine how this flexibility would help you map the thread block hierarchy to your problem depending on how your data was arranged. Okay, so in this particular case, we have a data structure coords that is indexed by molecule. Okay, so this is a structure that contains molecules, and each molecule, that second index is the atom index. Okay, so we have molecules, atoms, and then that third index is the x, y, or z coordinate. Okay, so coords, C-R-D-S, is 3-indexed molecule, atom, and coordinate. And in this particular case, what I'm trying to do is compute a distance matrix, that is the distance between all pairs of atoms within the same molecule. Okay, so I've mapped, because I'm computing this symmetric matrix, I'm leveraging one of the higher dimensional thread blocks, a 2-dimensional thread block, so that if we go back to this illustration, the blocks I'm going to use as an index into my molecule. So each block will map to a molecule, and each thread within the block will map to an atom. Okay, my problem is square, and so the 2-dimensional thread block fits very naturally to this type of problem. Okay, so hopefully that's clear how I'm mapping the thread block hierarchy to this problem. And you can see I don't have to, I wake up in the kernel, those first few lines, CUDA.threadindex.x, CUDA.threadindex.y, blockindex.x, I wake up with those initialized, right? And I'm simply reassigning them to tx, ty, and bx because they're shorter. So you can see the actual computation itself is on the last 3 lines. So for I in range 3 is referring to the x, y, and z coordinates of the atom. And then you can see the meat of the calculation is the second half of that long line. Chords bx is the block index. And you can see the first chords is indexed by tx, and the second chord's indexed by ty. So I'm taking that pair of atoms for that coordinate, either x, y, or z, computing the difference, squaring it, and returning the square root, and storing the result in edge feats. Okay, so the results matrix has a different shape, and you can see that that's indexed by block index or molecule by atom by atom. It's not necessarily super important if you followed my explanation of the algorithm. What's more important is that you see that we wake up with the CUDA provided variables, and that we can use the different thread block hierarchies to map it to a problem. And that's it. So in a handful of lines, I have a GPU accelerated CUDA kernel that will be just in time compiled and execute on the GPU. Now there's a little bit of extra work we have to do. We do have to make sure that there's space allocated on the GPU for the result. So I said edge feats is where we're going to have store the result of the calculation. So I need to allocate some space for that on the GPU. So I'm going to do that by allocating space. The call is device array, so CUDA.device array, and then I give it the shape and data type, allocates the space. And I'm going to assume for this case that we have the structure, the coordinates on the CPU, maybe they're in a NumPy array, and we need to transfer those in order for the kernel to do its work. We need to have that data on the GPU. So we transfer that data to the GPU with the calls CUDA.toDevice. That moves it to the GPU, and I get in return a pointer, structures underscore GPU, and natoms underscore GPU. These are pointers to the places where they're stored on the GPU. We launch the kernel. As I mentioned, there's a little bit of extra syntax with the function call itself, or the kernel launch. In C, that's the triple angle brackets. In Numba, it's simply the square brackets, which looks a little bit funny, but this is how we specify the launch configuration. So you can see I have the number of structures, last XYZ, by 29 by 29. That's the maximum number of atoms in this particular data set. And then the parameters. So I have my pointers to the coordinates array on the GPU, and my allocated pointer to my allocated space edge feats on the GPU. After the kernel is done executing, we copy the results back. So edge feats will be populated with our result, and edge feats underscore GPU copies that data, dot copy to host, copies that data back from the GPU to the CPU. And we're done. So with a relatively few lines of code, we expose the CUDA programming API in most of its glory, with the flexibility to move data back and forth, allocate space on the GPU. So this is the lowest level API that we can program with Numba, and it's more or less like programming in CUDA, and we don't have to leave our Jupyter notebook to do any of this, which is just amazing. As I mentioned, there is a higher level API. We can also program NumPy ufuncs, or universal functions. So in this way, we can write extremely simple kernels. They're really functions, and have it automatically vectorized on the GPU. So if you've worked a lot with NumPy, there are different ways. You may have even used the vectorized decorator to do a CPU vectorization over a set of operations. But Numba gives us the ability to target a GPU accelerator, a GPU, by specifying target equals CUDA. And in the same way that we write NumPy universal functions with the vectorized decorator, we can now write GPU accelerated versions of a universal function. The nice thing is that the kernel launch is simple. The data is moved automatically. So we can reap a lot of benefit for simpler algorithms when we don't need all the flexibility that's provided with the CUDA programming API. All right, so that's Numba. We're going to shift gears now and talk about RAPIDS. So RAPIDS is our open source stack for data science. So in RAPIDS, as I mentioned, we provide really two big things that I'm going to focus on. cuDF is a GPU accelerated drop-in replacement for pandas and for working with data frames. And cuML is a GPU accelerated drop-in replacement for many of the algorithms contained in scikit-learn. So those of you who've worked with pandas and data frames in the past, especially from inside a Jupyter notebook where the data frames are pretty printed, working with data frames is a dream. You have column names, the slicing is super convenient, the ability to handle various types of data within your data frame, doing complicated pivots and operations between columns, user-defined functions. It can get very powerful and it's extremely convenient. Of course, the downside is many of the operations for data frames are fairly slow. Some of them are fast, but if you're not careful and you don't know exactly how to use the syntax, it can be extremely slow, painfully slow. And that's really the motivation for why we developed GPU accelerated data frame operations, CUDA-F. So we intended this to be a drop-in replacement for pandas. So a lot of the syntax that you already know for pandas is essentially identical. So pick up a CSV. I've imported CUDA-F as GD, GPU data frame. gd.read CSV. If we imported pandas, be pandas.read CSV or pd.read CSV. Completely, we strive for interoperability with pandas, so we can go from pandas. If you're already working in a pandas data frame, you can go back and forth from pandas to pandas. So back and forth between GPU accelerated data frame and pandas data frame seamlessly. So there are some operations that we just don't cover yet. This is a relatively new product, and so we don't have complete coverage of every pandas operation. So it's really common in practice to go back and forth from pandas. Do your heavy lifting, heavy computation with the GPU accelerated data frame, and if there's some, operation that's not quite covered or you don't need the GPU acceleration for it, go back to the to pandas data frame and continue working in your pandas data frame. So seamless compatibility back and forth between GPU accelerated data frame and pandas. Most of the other syntax that we like is covered. The data frames are pretty printed, so within a Jupyter notebook, you still get the familiar printing of the data frames. Slicing operations are going to work just as you're familiar with in pandas. So, for example, using the slice notation, 14:17 gives me rows with index values 14 through 16, right? Not inclusive. Selections by column name, we can either do with the dot operator or with the standard string indexing, like a dictionary. Slicing by row and column works the same using the dot lock operator, loc operator. So in this case, I'm saying, give me rows with index equal from 14 through 21 and give me columns X, Y, and Z. So two-dimensional slice. And operations between the data frames. This is of course, the stuff we're most interested in. So doing these kinds of, in this case, a very simple operation between columns in your data frame are just automatic vectorization, right? This is where the power of the GPU is really going to kick in. Though surprisingly, and test this for yourself, picking up a data frame from disk, as in gd.read CSV, or you're asking CUDA-F to read a CSV file from disk and import the GPU data frame, is often significantly faster than the CPU version. So a lot of operations going on in the read CSV, just populating the data frame. Try it out for yourself. We can also construct Boolean series. So in this case, we're asking for this column norm greater than 3.0, and we get returned a Boolean series. And we can use that to slice data sets, slice a data frame, right? So I have my selection columns here, molecule name and atom, and I want to slice, give me the selection from my data frame using the select columns and that Boolean series where the norm is greater than 3. So you can see the simple data frame syntax that Pandas pioneered, all there, and you just reap the benefits of having a GPU accelerated data frame. Unique elements, and where it really gets exciting, I think, is that we can have user-defined functions. Okay, so we have the flexibility, just like we do in Pandas, to do user-defined functions between rows and have this sort of vectorized over our data frame. We can do the same thing with CUDA-F and have a GPU accelerated user-defined function that's operating on our data frame. So in this case, I'm defining this simple function, label mass, and it's going to take an atom code and return just the mass, in sort of a dictionary type thing. And applying that user-defined function over our GPU data frame is as simple as calling gdf.applyRows and give it my function label mass, tell it which columns are coming in, which columns I'm going to use, label, and then I pass a dictionary for the outgoing columns and a dictionary for any extra keyword arguments that are needed. And you can see applying this apply rows to my GPU accelerated data frame works as intended. So it's nice to have the extra flexibility to do user-defined functions. Apply rows works, hopefully, as you're familiar with in Pandas. And again, you just get to reap the rewards of having GPU accelerated data frames. CUDA-F also provides a large set of the vector functions. So we're talking about, max, min, clipping, absolute values. As we mentioned, the ability to define kernel functions and mapping that kernel function with apply rows. The nice thing about operating on data frames is we can string together a series of operations and very quickly achieve what we're after in a relatively small amount of syntax. So, for example, here I have this CSV file with these molecule names that identify what molecule they are, but of course the molecule names are strings. So I'm splitting the string on the underscore, I'm taking the second argument and interpreting that as an integer. And on the line with the comment hash by molecule, construct a hash out of that integer and taking the mod 4 to construct a test train split. So in 4 or 5 lines of code, doing what would take me in C significantly more effort, and of course as compared to Pandas, get this done in GPU accelerated way and have it take a quarter of the time or less. So as I mentioned, so that's CUDA-F. cuML, which is the other major piece of RAPIDS, provides a handful of machine learning, of the most commonly used machine learning libraries. and we're constantly adding more algorithms. So I'm not going to go through all of these, but I'll just highlight a few. So for example, QML provides k-nearest neighbors, supervised machine learning for classification. dbScan, unsupervised clustering. K-means clustering, another unsupervised algorithm for clustering. Singular value decomposition. Okay, so this is a matrix factorization routine. And in fact, we provide truncated singular value decomposition. So what's common, in many cases, the reason you're doing singular value decomposition is because you're trying to approximate that matrix M. So M, what SVD does is factorize M into, well, it's showing you U, sigma, and V, where the sigma is this diagonal singular values. And then you approximate M by truncating the number of singular values that you represent. So that's what we mean by truncated SVD. Principal component analysis. Everybody knows what this is, widely used for dimensionality reduction. We're really trying to understand the axes that explain the most variance in our data. And then in the case of dimensionality reduction, we ignore the rest, or we project into that basis. XGBoost, supervised decision tree. And as of version 13.0a, this is the complete list of algorithms that we support. So in addition to the algorithms that I've mentioned, we have t-SNE, ordinary least squares regression, elastic net regression, logistic regression, optimization algorithms such as stochastic gradient descent, random forest, both classification and regression, support vector machines, Kalman filtering, widely used in aerospace, ARIMA, widely used in financial services or quant finance. And we're updating this list very regularly. And in fact, tomorrow this list could be extended. So be sure to keep up with what algorithms. If the algorithm of your choice is not on here, shoot me an email and let me know. We're always interested in hearing what algorithms people are using and providing that feedback to the RAPIDS team, and hopefully get that algorithm implemented in the next version or two and get it GPU accelerated. Last thing I'll mention is you should certainly check out our container repository. We offer more than 50 containers that are optimized, GPU optimized. These are containers for deep learning, machine learning, and high performance computing. So certainly check out our container repository at ngc.nvidia.com. And hopefully you'll find the application container that you're looking for. With that, I'll wrap up. Thank you very much, and I'd be happy to answer any questions.
Thanks, Abe. Yeah, there was a question in the chat that was kindly answered by another attendee, but if you want to take a look just to make sure, it was, can we launch kernels with max possible threads and blocks for any task, leaving some threads idle?
Yeah, so if I understand the question, can you have more threads than you have work to do? And the answer is yes, definitely. And the way that that's typically handled is by checking the bounds for the array that you want to perform work on. So say my data array in that example, I showed 8 elements in there, right? Because it was just convenient. We had 2 blocks, 4 threads per block, and so that's 8 threads. So I was showing 8 units of work to do. But we could certainly map that same launch configuration to 7 elements of work to do, and we would simply bounds check to see, you know, is my thread index going to map to a data array that doesn't exist? If so, if I am out of bounds, then simply return. Don't do anything. So that thread will be quote unquote idle. It just won't do anything. And so that's how we would handle a thread block mismatch like that. Very common.
There was another one, will Rapids work on my GT 1030 in Windows? Is there still no support for NVIDIA cards in newer Mac OSs, even for scientific purposes?
So the 1030, the official answer is we support Pascal, Volta, or higher architectures. You know, unofficially, your mileage may vary. You can try it and check. And the Mac support, I'll have to check on Mac support. I don't know that the answer off the top of my head for that.
Let's see. Some folks are asking about how to self-mark attendance. I'll send that in an email to the registrants, and that'll help them.
Okay.
One more question. What is the performance of Numba compared to OpenACC and CUDA in C++?
Oh, that's tough. It's tough to compare performance between the different libraries. So let's say OpenACC to CUDA. While this is not in general true, in many cases, so what OpenACC is doing under the hood is taking a best guess at what a compiled CUDA kernel would look like, a perfectly optimized CUDA kernel would look like for the algorithm that you're trying to parallelize. Many cases it's right, and if you were to write your own handcrafted CUDA kernel, performance would be the same. But sometimes it's not quite as optimal as a hand-tuned, hand-optimized CUDA kernel. So what you get with the convenience, sometimes there's a little bit of a penalty. You could do a little bit better if you handcrafted that CUDA kernel. Making the comparison for, you know, operations that we're doing in RAPIDS to handcrafted CUDA. I mean, everything in RAPIDS is a CUDA kernel under the hood, right? There is C code, handcrafted C code under that Python API. So I suppose the answer there is it's the same, because it is handcrafted CUDA code.
Okay, I think that's it. Please send some questions via email if you still have some questions. Thank you very much, Abe, for the presentation. It was excellent. And thanks everyone for joining. Bye.
Thanks so much.